Patterns in the hundreds chart. Only 4 questions this time. Whoa. Which 2 statements describe the patterns in the shaded part of the hundreds chart? Interesting. I have not actually looked at this topic yet. This is brand new to me. So I'm looking at the pattern, and before I look at the answers, let's not look at that yet. Which 2 statements describe the patterns in the shaded areas? So what's happening in the shaded area? We're looking at the purple sort of diagonal area, and it looks like it's adding 9. Is that right? 3 plus 9 is 12, plus 9 is 21, 6 plus 9 is 15, plus 9 is 12. I think that's what we're looking at. I wonder why that is. So there are 2 answers. Each shaded number is the product of 3 and a whole number, which means they're all divisible by 3. Are they? Are they? I don't see any numbers that are not divisible by 3. Oh, crap, we haven't done that in a while. Let's talk about how to figure out if a number is divisible by 3 if you don't know, all right? Really, really fast. It's nice and simple. Let's say I have a number like, I don't know, 1,267. I have no idea if this is divisible by 3 or not. I just made it up. The way to figure out if something is divisible by 3 is to add up all of the digits. So 1 plus 2 is 3, plus 6 is 9, plus 7 is 16. And then check. Is this divisible by 3? Well, I happen to know for a fact that 16 is not divisible by 3, so the whole number isn't. Now, why does this work is something I'm going to make a separate video on at some point. There is obviously mathematical structure behind it. It's not like magic. I could also continue to add them together to get 7, which I definitely know is not a multiple of 3. So anyway, looking at all of these numbers, it does look like they are all multiples of 3. Let's see. To get to another shaded number, add 10 and then add 1. 3 plus 10 is 13, plus 1 is 14. Well, that's clearly wrong. Nathaniel, welcome. Glad you're here. Just talking about some 3rd grade math. Each shaded number has a multiple of 3 in the ones place. Well, that's obviously wrong. Look at 48. 8 isn't a multiple of 3, so that's wrong. So that means A and D have to be the right answers. This is something, by the way, this problem is one that is likely to take a student who's not used to thinking this way a long time to figure out. And that's valid and that's important. But, you know, I know grown-ups who have a hard time with this, so don't give your kid a hard time if they're having a hard time. Complete the pattern table. Well, it looks to me like going down, they're adding 10s. So 28, 38, that would make this 48, and that would make this 36. Not bad. Some of these are easier than others. Odd numbers. Do they always, sometimes, or never have an 8 in the ones place? And yes, right now, we are going to talk a little bit about the definitions of these very, very simple words because, again, A, 3rd graders, and B, we don't use these words the same in regular English as we do in math. In math, when I say always, I mean no exceptions. None whatsoever. In math, like, you know, people talk about Seattle like it rains all the time, even though it doesn't. They'll say it always rains in Seattle. And then you walk out and say it's not raining right now. In math, that's enough. You don't have to do anything else. If you can come up with one example of whatever it is failing, whatever statement, whatever thing, then it's not always. Same deal with never. Also, no exceptions. If you can come up with, for example, one single odd number that has an 8 in the ones place, you can't, but if you could, then the answer would not be never. It only takes one, what we call counterexample. Okay? So sometimes is usually the most reasonable answer, but not, again, or in real life. In real life, sometimes is usually the best answer. But in math, you know, we have rules that don't have exceptions. For example, you can't have an odd number with an 8 in the ones place, because if there's an 8 in the ones place, that makes the number necessarily even. And very helpfully, they have highlighted all of the odd numbers here so that you can check, are there any exceptions at all? Or is there a single purple square with an 8 in it in the ones place? And the answer is no. Which two statements describe the patterns in... Okay, so it looks like... What are they doing? It's 1 and 100. And then it's adding... It's not adding 9. What is it doing? I don't really see the pattern here. The shaded numbers are all... Oh, so it's okay. So we're not necessarily coming up with a rule. That makes sense. Because that's adding 9. Oh yeah, it's adding 9 all the way up. 1, 10, 19, 28, 37. I'm a math teacher. I know these things. So the shaded numbers are all odd. To get to the next shaded number, add 10 and then subtract 1. Well, that's the same thing as adding 9, right? The shaded numbers aren't all odd. There are definitely even numbers in there. And to get to the next shaded number, add 9. Nathaniel and Hartman, well done, both of you. Thank you for keeping me sane. I don't know why the 1 and the 100 threw me off, but there it was. There it is. These things happen. And that's that. That's a good one. That was a really, really good one. You know that it's a really good topic if it makes me, a teacher of 20 plus years, stop and scratch my head a little bit. I like problems like this. Now we're going to